This is my last video in my module on finding areas of triangles using different formula setups, or if you had a side angle side case, or angle side, or side side side, different ways of finding areas depending upon what information you're given. And in this case, we're actually going to use everything we've learned to find the area of a parallelogram if the angle, if we're given certain information about that parallelogram. And in this case, we say the angle between two of the sides is 135 degrees, and the two sides are 20 and 15 inches respectively. So the thing is, when you talk about parallelograms and how they relate to triangles, let's go ahead and start by sketching this. We say the angle between two of the sides is 135 degrees. So this would be something like this. We have a parallelogram, opposite sides are parallel to one another, and we're being given the fact that this is 135 degrees, okay? Also this, if we were to sketch in the rest of this now, kind of, I don't know, just a rudimentary sketch, but we would say we've been given the fact that the sides are 20 inches and 15 inches respectively. So we want to find the area of this. The interesting thing is we could actually drop in some diagonals to give us assistance on this one. So in terms of what do we know about this parallelogram? Well, first of all, opposite sides are not just parallel, but they are congruent in length. So we know that if the top's 20 inches, the bottom's 20 inches. If this side's 15 inches, this side's 15 inches. Where do the triangles necessarily come from? So here's what we can do. We can drop in diagonals. We have this diagonal right here, or we have this diagonal right here, or we have both of them. But in this case, if you think about this, which diagonal would be, most helpful in this instance? We could actually drop in this diagonal right here. And the reason why it is most helpful is because if you notice, like we mentioned, this is also congruent to the top side in terms of length, congruent lengths, or equal lengths. Essentially, you could see that we have a triangle in this instance, not just any triangle. We could actually find the area of this triangle because what we have is a triangle in which we know two sides and their included angle. So here's what we have. All right, this would mean that we have the area. Remember, we're using the capital S here in this case to represent area. We do not want to confuse this with, say, vertex A of a triangle, and that's why we avoid using A. But we say the area of this, in the side angle side case, we were using the formula 1/2, say, AB sine C, or, BC sine A, or AC sine B. In this instance, though, all we need to know is that we have 1/2, the two side lengths, so that'd be 15 inches and 20 inches, and then the sine of their included angle. Okay, so 135 degrees. One thing that I haven't done in this video that I'm going to do now, because I realized that it's something that I preach quite often, and it's going to be really helpful for you guys to see where I got my values from, is this. What if we were to necessarily take this triangle over here and kind of sketch it off to the side? And this isn't a perfect replica, but to say that this is 135 degrees here is what we know. We also know that this is 15 inches, as well as 20 inches here, is label out the sides, okay? So I tend to call the largest angle vertex C, so it'd be lowercase c. We also know that maybe we'll call this one A and this one B, so we can refer to this side down here as lowercase b, and this side here is lowercase a. But in terms of how I knew to use this formula here, notice that we know the lengths of sides A and B, which are these two side lengths here and here respectively, as well as their included angle, which happened to be angle C, so no surprise. This is, as far as finding this goes, we could actually get an exact value for this. This is fun. You don't get to do this every day with nice numbers like this. We'll use a calculator in a moment, but what if we said 1/2 times 15 times 20 times sine of 135? Well, first of all, we could take this 1/2 times the 15 or times the 20. I happen to know that 1/2 times 20 actually makes this into 10. And then 10 times our 15, we'd get 150 square inches, and this is times the sine of 135. Anybody, though, who's taken a trig class knows that 135 degrees right here has a reference angle of 45 degrees. And so when we take the sine of 135 degrees, you're going to get the same thing as if you took the sine of 45 degrees. It's just that it's in the second quadrant where it terminates, and so our sine value actually does come out to be positive. By the way, the sine of 45 degrees is the same thing as radical 2 over 2. So we're taking 150 square inches times radical 2 halves, which is the value of this. And so, I don't know, multiplying these out, 150 and the 2, they cross cancel, and we get 75 square root of 2 inches squared. So 75 radical 2 square inches. So this is our area as an exact value. Hey, we can actually use a calculator now, which is what we sought to do in the first place. But I've got my calculator out. Here we go. we could say, all right, sine of 135. So we say 135 degrees. Make sure you're in degrees. Sine of that times, we had 20 to begin with right here, times 15 times a half, or 0.5. So we get 106.066-ish, 106.066 inches squared. And just to check this, what if I took 75 times radical 2? I just don't want to be that shocked on this one, but if I said 2 radical times 75, makes you feel kind of good when you get the right answer. So anyways, this is an example of how you might find the area of, say, a parallelogram in which you don't know the height of the parallelogram, because parallelogram areas, this is base times height. We could just use triangles instead. Just make sure you're dropping in altitudes and labeling out your sides. Maybe draw your triangle off to the side. Cheers.